Hi, my name is Wei Yang. I'm going to present our work of using MPC for human-to-robot handovers of unknown objects on behalf of my collaborators.
In prior works, the grasp generation, grasp selection, and motion planning were conducted independently. The grasp could be inconsistent over time, causing the robot oscillation. In this paper, we propose to use MPC to tackle this issue. There are 4 stages that the robot can be in. First, the robot will wait for the human to appear, retract the human body, and segment the object point cloud and generate grasp by GraspNet. Then the robot will approach to a standoff position and finally grasp the object. Finally, the robot will drop the object onto the table. We use MPC to optimize the joint acceleration by minimizing a cost function with a set of constraints, including the manipulability and the stop cost, the collision avoidance which avoid the robot to collide with a hand or occlude the hand from the camera, and the bounds for position, velocity, and acceleration. We use a straight line cost which encourages the gripper to move as a straight line towards the target gripper pose. We also have a handover cost which has 2 implementations. The single grasp cost encourages the gripper pose to be as close to the target grasp as possible. The grasp set cost will take the whole grasp set as input and minimize the minimal distance between the current gripper pose and each of the grasp. As demonstrated in this video, encoding all grasps inside the MPC cost with each time step enables the system to reactively reach the closest grasp in the motion space. Additionally, we learn to predict a reachability score for each grasp, which is a measure of how far the robot is to a singular configuration. Intuitively, a grasp is reachable if it has a positive reachability score, otherwise it's unreachable. We trained a classifier to detect when a contact between the gripper and the object happens. To facilitate training, we collected a dataset of humans interacting with a moving robot. The detection is then used to trigger the closing gripper action. We conducted a systematic evaluation with handovers from 3 different locations with 3 objects. For each experiment, we repeat until 3 successful trials have been recorded. For each trial, we hold the object in a different way, and we reported the average approach time and the success rate. While the previous system struggles with smaller objects, such as the pepper bottle, our system is more robust. Prior system also has difficulty to grasp the big box from the right position. In general, our system has higher or similar success rate for these cases with much lower execution time. For reactivity experiment, where we rotate the object 45 degrees after the robot starts moving, we observe similar improvement with our system. Specifically, both reachability model and the goal set cost promote faster approach time while maintaining a comparable success rate. Finally, we conducted a user evaluation with 4 users. Each user did 2 rounds of handovers to interact with 2 systems without knowing the details of the system. We counterbalanced the order in which users interacted with the 2 systems to avoid the bias. After completing all interactions, users were asked to rank the 2 systems and share their opinions. 3 out of 4 users thought our system is more predictable, less jerky, less aggressive, safer, and more comfortable to work with.
Please visit our website for more videos and experiments. Thank you.